So thanks a lot for the invitation. So Tom asked me to make a very basic presentation, so I will do that. But if it is too basic, please tell me. Okay, so and of course you can interrupt in any moment, and that's it. So it's very basic, maybe too basic. So tell me if it is too basic. Okay, so what I want to speak about. So Grassmann integrals. So you will see what they are, but essentially what I want to say is that most solutions in two-dimensional models are based on determinants, okay, or Pfaffians. So like the Dimer solution or the Ising model solution of Onside. They are written as determinants. These determinants are simply quadratic Grassmann integrals. They can be written as Grassmann integrals. I think the first who wrote in terms of Grassmann integral is Hurst, I think in the 60s. There is a journal of chemical physics.
Sorry?
Hurst, H-U-R-S-T. Hurst. Yeah, okay. So in the 60s, he wrote this Grassmann integral for the Excel solution. Then these free fermions are also found by the transfer matrix approach of Lifshitz and Matrix. But Hurst was using directly the Grassmann integrals. Okay, so the point is that when you have non-solvable models, you have to you don't have any more Gaussian Grassmann integrals, but you will have quantity Grassmann integrals. So this representation in terms of Grassmann integrals is very well known since I think the 70s. The point is that not so many people used it in the rigorous framework, but now there is a lot of developments of these Grassmann integrals with quartic terms. And now finally we can use this representation in terms of interacting Grassmann integral for the Ising model. In a sense, it's a bit too much because these techniques for Grassmann integrals were developed for quantum field theory, which in a sense is a more difficult problem, but then can be applied to statistical mechanics and in the sense, okay, the sense you are using atomic bombs for a simpler problem, but it's effective. So maybe you are using all this Bellic metaphor these days. But anyway, so it's something natural to use this metaphor. But okay, this is what I got. So okay, let me recall what is the Ising model. So the Ising model is just this. This is just the nearest neighbor. So let me say from the start, these simplified features of this model, right? We have the spins, we have two values. It should represent some dipoles which don't have two values, but I mean this model is like that, and you have only nearest neighbor interaction. Okay, so that is the Ising model. So an important observation which has to be done is that the quantitative prediction of this model are quite correct, in particular of the critical exponents, even if the model is very rough. So this is a phenomenon which is called universality. Okay, so you have you have quantitative prediction using a very simple and approximate model. And this is one. So one could say what happens here. It's very natural to say why I consider only nearest neighbor interaction. Why I don't consider more. Why I don't consider instead of 2 states 4 states and so on. You want to expect that it is an experimental matter of fact that you get a lot of properties unchanged, but it's a part of the problem. So anyway, let me just recall this very basic definition. So lambda is a square box, periodic boundary conditions. So the averages are just the average using the Gibbs measures. So the observable are done making sum over all the possible states. So in particular, one is interested in averages of this spin or averages of the energy, for instance, like this. Okay, this is the partition function. And it is well known by Onside that this Z can be written as 4 Pfaffians, which are objects related to determinants.
What is the average? The average is of all configurations?
Yes, it's all the possible spin. Yes. You define all these sets of spin and you sum of everything. So that's the Ising. So another model which is very much related to this Ising model is the Dimer. So the Dimer model, maybe since it was my picture, is simply a set of edges, right? You have this bipartite lattice, and then you cover by edges. And there is the constraint that each vertex has to be covered exactly once. Okay, so exactly once. You cannot have nothing like this. So this is a dimer. Okay. Then you can define the partition function for a dimer. You sum again over all the possible configuration of the dimer with this weight. Okay. So for instance, if you have a dimer like this, then you will have TB, or you have this, or you have this. So very simple. If vertical and horizontal are equal. Okay. So you see simply these two possible configurations.
Edge, you have a weight there.
Yes, TV, I call it TV vertical and horizontal. Okay. Of course, I can consider in this case I put TB, so this would be T13, T24 plus T12, T34. Okay, and that's it. So this is the partition function. Again, Castellan in 62 showed that Z can be written as sum of 4 Pfaffians of this matrix. Okay, there is an extra solution also for this node.
What does it mean, Pfaffian of the matrix?
You have force because this is a problem of boundary conditions. So this 0, 0 means periodic in this matrix. This means periodic, antiperiodic. This means antiperiodic, periodic. This means antiperiodic.
What does it mean, Pfaffian of a matrix?
You have 4.
So definition of Pfaffian.
I will tell you.
You define a
Yes,
Pfaffian?
yes, I will tell you. Yes, L by L.
But there's a specific matrix which you can write down.
Yes, this one, K.
Compute it.
Yes, you can compute it. But you will see it's much easier to write in terms of Grassmanns. I can show you the definition, something like this, just to. So this I take it by Wikipedia. It's not something very right. So the Pfaffian of this is defined for any antisymmetric matrix. So for instance, 2 by 2 is this, 4 by 4 is this, and this is the
Square root of the determinant.
Yeah, it's written here. Yes.
But it's got the right sign.
Yes, it's the square root of the definition. So I think this definition, the sum of all the permutations. So it's very easy to, okay, by the examples, right? So but you will see it's very natural to write in terms of Grassmann. So the solution of the models is written. So it's, in fact, in the bounds, this relation is very important because then we will use bounds for the determinants for proving the things. Okay, so nothing mysterious. I could avoid the Pfaffians, but okay. So let me see.
Do we assume that the energy just depends on the orientation of the diagram?
Yes. So in fact, now, yes, okay. Anyway, so you can define also the height. Okay, what is the height function? So again, you have this complicated definition here. The difference of the height is associated to the center. Let's see what's this picture. Okay. So for instance, 0, minus 1, 4, minus 1 half, minus 3, 4. Okay, I don't know if you can see this. So this is 0, this is minus 1 over 4, minus 1 over 2, minus 3 over 4. So this is the definition here, right? You have to sum, for instance, if you go.
I didn't understand what the chi is.
Yeah, just a second. So for instance, suppose that x is 0 and y is this point here. Okay, then C is a path like this. Or I can consider also another path like this. Okay.
So x and y are getting their values
In the center of that, yes.
in the dual.
In the dual, yes. I use the same name, but it's the dual. Yes. Yes, and you see, it's again, you can verify. Chi, okay, sigma is plus or minus depending on this path cross B with the white side on the right and left. I will show you what it means. Chi is 1 if you B is occupied. Okay, so for instance, here, if I'm going from here to here, you are crossing this. But here this is not occupied, so it's 0. Instead, from going from here to here, you cross this. Then chi is 1. From here to here, it's 0. From here to here, and then you must find always the same value. And then sigma, you have to look to the left and right, right? So if you are going from here to here, then you have the white in this direction. Okay, so it should be plus.
It's an orientation.
Yes.
In the orientation of the path.
Yes, you see. So you get minus 1 over 4. If you go from here to here, you get 1 because chi is 1 minus 1 over 4. So you have 3, 4. Okay, and then you arrive here. Then you arrive minus 1 half, and you arrive always to the same value. Okay, so it's a very nice So this is the height function. So what is very important is independent on the choice. So this allows you to give a random surface interpretation. So you can see this dimension as you have a third dimension, and then you have fluctuating surface. Okay. Okay. So also in this case, you can solve it by Pfaffians. Okay. So now immediately the Grassmann variables. So what are the Grassmann variables? Are very simple. They're so at this level. Let me say that the Grassmann variables are, in a sense, useless. It's just a way to write these determinants of Pfaffians. That's it. So it's an interpretation at this point. I don't think it helps a lot. Given a final set of Grassmann variables, right, which are anti-commutative, the Grassmann integral is simply this. It's 1. Otherwise, you see, this is the only possibility in which is 1 up to permutation. Otherwise, it will be 0 because you will have 2 of the same or less. Then you will get. So this is the definition. The Grassmann integral is only this. The product from 1 to n, the psi n, psi 1. This is given a finite set of Grassmann integrals. That's it. So you see immediately that if you apply this definition, then the Pfaffians is exactly given by this formula. Okay, you simply expand this. Okay, so for instance, if you have 1, if you suppose that you have, unfortunately, now I don't have, I cannot. Okay, anyway. So for instance, if we have something like this. Yeah, just make an example. It's very simple. This would be. That's it. Because you expand this, the rules is that you have to expand the function. Then the only case in which it survives is psi 1, psi 2.
Just the top form you keep.
Yes.
These are like. Yeah. It's like differential forms.
Yes, isn't it?
And then you just keep the top form.
Exactly. But the interpretation of this is that is very much reminiscent, right, of a Gaussian measure. Even if, in fact, if this would be variables, then you would have something like 1 over determinant. Instead, here you have the Pfaffian that we said is related to the determinant at numerator, right? So it's something like this. But it's very easy to verify. Simply expand this. And then you will get that the only terms which remains are these ones. Okay, it's just something very immediate. Okay, so I repeat, you have a matrix here, antisymmetric. You expand, you use this rule, you use the antisymmetry, and then immediately you will get this relation.
That's a commutative, which is
Anti-commutative.
on the top line.
Yes,
It's an
anti-commutative.
anti-commutative.
Yeah, in fact, because you need these signs.
Does this thing play nicely with complex numbers? So if I multiply the antisymmetric matrix with an I to make it self-adjoint, does this mean that I just get I times the Pfaffian?
Yes, because it's I'm not sure.
It's even anti-symmetric, of course.
We must be.
Because
You get not 1 over the determinant, but the thing is, you can, so I think in the Verizon, in random matrix theory, when you want to divide by determinant, then you use these
Yes.
supersymmetric variables.
Yeah, but that
was later. That was
yeah. This would. No, I will not do that. I want to be basic. So this is exactly okay. If you want, as I said, this is completely useless at this level because we know the answer, right? We know that the solution is a Pfaffians. So why we want to write in this way? Okay, we will see. But at the moment, it's just another way to write a determinant. That's it. You don't have to think nothing deep. Only that if you like probability, this looks very much like, so for instance, look to this formula, right? The integral of this times this psi is the Pfaffian of G. And G is the matrix A minus 1. Okay, so you see, this, for instance, looks very much what is called weak rule, just that you have the signs. You have the Pfaffian, so you have a lot of signs between the terms. And these are simply, it doesn't add anything. We know the solution of the Ising model and the dynamics. They are Pfaffian, so we don't get anything by that. So just another way to write the same thing. That's it. Okay, so I hope this is clear because this was Tom asked me just to make an introduction, but introduction is very short. I mean, it's another way to write we know that the solution of the Ising model is a determinant or a Pfaffian. Maybe we would like to write in this way. Actually, Ernst derive the Pfaffians in this way, I would say. So it's okay, it depends on the taste. Maybe you prefer to derive the solution in this way. Right? So anyway, I hope it's clear. Right? So if you make two examples, you see, you immediately recognize this formula, right? Because when you expand this, then you will have lot of terms, quadratic, but the only terms which remains in this one with the signs. So you get exactly the sum of all the permutations. Very good.
With the weight, with the
sign, which is the crucial. And then also this formula is very nice. You can derive this formula in a one line using these Grassmann determinants, make it change your variables. Okay. So for instance, let's go back to the Pfaffians, to the dimers. So the representation of in the dimers case is simply this. With this derivative is simply cx plus e1 or dx plus e2. E1 and e2 are the versors. Okay. But you immediately derive, you understand exactly. So let me make a very simple example, even if you know the camera. But so 1, 2, 3, 4. So you see immediately that when you expand this will be something like t vertical. Okay. You expand, then if you choose, for instance, this.
Everything that you just wrote is in the exponent.
Yes, I don't know how to.
Yeah.
So when you expand, for instance, if you choose this, then you need this, otherwise you get 0. If you choose this, then you have this. Okay, but it's very important that here you have an I. So here you see you get 1, 3, 2, 4. Here you have 1, 2, 3, 4. But the dimers are some of stuff. So you get I squared minus, which is plus. Of course, this is very easy for 2 by 2. N by n is more complicated, and this is this famous Castellan lemma of 63. Okay, because right, it's very easy to see that you can. There is clearly a correspondence between the dimers and this representation, but these objects are anticommutative. So what is not obvious that you get the signs, which are the same. Okay, and then you need an argument. Okay, otherwise the Castellan lemma would be trivial. Instead, is a nice result.
And it's only true in 2 dimensions.
It's only 2. Yes. But it's okay in this case, right? It's clear because you have a nice square, so it is the I here.
2 dimension here means that you have
x 1 and 2, right? So
you have just 2 directions.
yes. All of what I will say is in 2 dimensions. Okay. So of course this is very rough because then I have to take into account boundary condition and so on. But so you see, but then people is very happy because they say this is simply a very complicated way to write tv squared to to squared. Right? So it doesn't seem a very good idea to write this in this way. Right, so it seems complicated. It's very simple. It's T1. If you put 1, it's simply 2. It's a very complicated way to write 2. Okay, so maybe it's too complicated. But then people likes because this looks very much Dirac fields. Right. So even if we are not speaking of fairness or nothing, but if you look formally, this reminds a lot of what are called Dirac fairness in quantum field theory. But you don't do simply the definition of the Pfaffians. Okay, so it's a sort of magic. You don't do anything and you immediately get these actions, which looks like a quantum field theory. This is the magic.
You got a direct, discrete Dirac.
Discrete Dirac, but we have not done anything. It's just another way to write the Pfaffians. Okay.
For dimers.
For dimers. So if you want to write the dimer correlations, so now is a computation I could do. You make the derivatives of this log z. So the dimer correlation, you have to make the average of this chi with the weight.
Chi is now
chi is 1. Yes, you have the sum over all the possible configurations. Then chi is 1 if you have B, for instance, it is an edge. So if the configuration is occupied.
It's just the indicator.
Yes, it's just the indicator function. Yes. Okay. So you see, it's very easy to see that you can derive this making derivatives of log z, because the only terms which survives if you have the TB. When you make the derivatives, so this is the definition of dimer correlation. Then you have to make derivatives, okay? And then of course, if you use this formula, then you will get this. So again, I hope it's clear. So we are not doing anything. We are just using the definition of the Pfaffians. We are simply apply the definition. But then you pin the psi, by definition, is simply this. I call this, I'm using this sort of probabilistic notation, even if it's just names, okay? Okay, then you see, so you see everything is very exact. It's exact, maybe there's a coefficient here, but it's just exactly these truncations. So the diagonal correlation is simply the integral over this pin the psi of this 4 psi. It's just algebra. And this pin the psi is this. It is clear up to now because this is really the basic stuff, but I think it's important that people understand that there is nothing. I mean, it's just the definition of determinants. But the outcome is nice because then you have the average of 4 psi. It seems quantum field theory, but even if it is not. Yes. So now you compute the 2 points. This is also very easy to get this formula. It's also this a very easy computation. You pass to Fourier transform.
What was the line with the capital T there? In the
T means truncation. Is this 4 minus the?
It's the two pairs together.
It's like
minus
the variance.
minus the
Yes.
product. of the
It's,
two.
yes.
covariance. What is
The
the
covariance. No, psi minus psi.
Okay, thank you.
Then you can copy the 2 point, right? And then you see this is the 2. You immediately get this. Even this is very easy, right? Because this is a sort of Gaussian. So you pass to Fourier. You get pk. Then now it's diagonal, so you get the inverse. And so you will get this. So now you see this has 4 poles. So it's essentially this has this sort of this form here, right? Conformal structure with this sign. Sigma is plus or minus. Then you can, by that, you use the definition of the Grassmann integrals. This is the product of 2 pairs. And then immediately you get this formula, which is the dimer-dimer correlation, okay, so this is the dimer-dimer correlation in the dimer mode.
So you just written down the covariance in Fourier space.
Yeah, that's it. Yes. It's nearly one line, right? So you see, here you pass to Fourier, then you get k, e to the ek psi minus k. Then you use you change variables, you get the sine of so. Okay. So you see, these are the famous critical exponents, 2. So you see, the dimer-dimer correlation, the case is 2. Okay, it's the critical exponent. So now you can compute also the 2-point height correlations, and then you simply make the sum, and then you get the log times 1 over pi squared. So it's interesting that then these surfaces are asymptotically Gaussians. Okay, and is what you get. So something important to stress is that it seems from this formula that there is a singularity at z equal to 0, right? But instead you can use the fact that you can consider this is a paper by Kenyon, Kumpf, and Sheffield, they compute that. You can use, so this is a y. You can use 2 different paths. So this z is never small. Okay. Otherwise you don't.
What's R there? Capital R? You get.
R is a correlation, it's a constant, it's smaller than a constant, it's not diverging.
Okay.
So you're just insert here this formula plus higher order, which are integrable. So even more, if you insert this here and you use these signs, then this piece oscillates and doesn't contribute. So it is this R. Only this part contributes.
So when you say higher order, it's when x is close to y, I am not.
This means this is constant.
This is at large, you're looking at
Large distance.
Oh,
Large distance. But what is important is that even more, only this part here contributes to these dominant terms.
Okay.
This is subtle because here you have a sign, here you have a sign, but here you have also signs. But the signs here combines with the signs here and disappears. And this is the real divergent part. And instead, here, due to the signs, you have contributed to this R, which is
like what?
What constant?
O1?
O1, yes. Okay, so let me say a bit quickly because otherwise I'm still in the non-interacting case. Ising model something similar. The reason why people introduce the dimers is that are simpler. In the Ising, you have also these non-diagonal terms. So it's not, so you see in this case, one says the model is critical. It always goes as 1 over zeta square. Instead, in the Ising model, only at the critical temperature, you will have a decay, which is power law. Otherwise, you have an exponential decay. But again, you write this exactly the same computation. You arrive to Grassmann variables, and that's it. Okay. So so now we arrive finally. So at the moment, this Grassmann integral representation doesn't use. It's not very useful. The point is, what happens if I consider perturbation of these models? So then they will be not anymore solvable. So suppose that we have a term like this. It's very, by the way, a term like this with a short range interaction, this is exact, for instance, include the case in which we have next to nearest neighbor interaction, for instance. There is no reason for which you can exclude physically why you should not take into account next to nearest neighbor interactions. Other possibility are you can consider two Ising model plus a V. Okay, this choice includes what is called the Ashkin-Teller model. The Ashkin-Teller model is a model in which we have not the spin says not two values, but four values, A, B, C, D. Okay, so you can write in this way. Or another model which is called 8 vectors. There are a lot of models which we can write in this way. Or you can consider interaction of the dimers. Okay. For instance, this is a plaquette. So you add this weight in the plaquette, and P is 1 if you have two dimers parallel, and otherwise not. Okay. So all these models are non-free fermions, let's say non-quadratic in the Grassmann variables, can still be solvable by better answers, but we will not speak about that, but generically are not solvable. So the point is, what happens to the exponents, for instance, or how can we compute this stuff? Okay, if there is no solutions. So at the moment, the only way in which you can get information, for maybe one day will be other method, but at the moment, the only way in which you can get information on the exponents at criticality in these models when you don't have a solution is using this Grassmann integral.
When you say no solution, you mean no exact formula?
Yes. Yes, no exact. I mean, even less. You can have a solution which is not a determinant, like better answer.
A non-determinant.
Yeah, now I mean just solution determinantal solution. But then
you're not defining a bigger class of integrable systems.
No. I want to go in the opposite direction. I want just to say I don't want to care solutions. I want just to consider, because this is in a sense I find more physical, right? So why the nature should care about solutions or not? I mean, these models should be genetically they should be models holding if they are solvable or not. Right? So I want to get the universality hypothesis says that you should get the same behavior if you have solvable or not, at least for critical property. So that's the universality. And then so if you use too much the exact solution, then you are in a sense, it's strange in a sense. Okay, so it's this. Okay. So let me introduce some exponent. For instance, for the calculate Ising model, I will come back. So I will call energy the sum of the spin. You remember that here I'm considering this sum sigma sigma prime, so two Ising models with a perturbation, with an interaction quartic. So this is a notation of Kadanoff. You call A the sum of the energies, sigma and sigma prime. You call crossover the minus. You call polarization, sigma sigma prime. Okay, and then I will call XC, XR, and XP the exponent at the critical point. There are also complicated relations between all these exponents I don't want to enter. For instance, the dimer and the Ashkin-Teller are related. So the energy correlation of the dimer are equal to the exponent. So the energy correlation of the Ashkin-Teller is the same as the exponent of the dimer. The polarization exponent is equal to the exponent of the electric correlation in dimers. So there are these are exact relations. Okay, so but it is interesting to point out.
So when you're talking about these Ising model, we're talking about
yeah, I mean, sorry, the second line, this line here. I'm connecting this and this. Okay. Okay, so finally, what are the non-determinant models? So for instance, suppose that we consider these Ising models with these dimers with perturbation, right? So you can write in this way. This is here. You can write in this way. So you see immediately you make the trickle derivatives you've seen before, and you write in this way. The partition function is spin psi e to the v. Okay, so you get immediately a Grassmann integral which is not anymore quadratic. You get a quartic. Okay, so genetically, right, for any v, this is exact. You have simply to make derivatives and you immediately get this. V sum of terms of higher order. So you break immediately the solvability. And then the energy of dimers can be written this way. Then. Okay, so the average of that. So now let me say that there is a deep difference between energy, which are local expressions, and or from polarization of height, which involve non-local. We will see what this means. Okay, so let me make a comparison between, for instance, phi4, right? So this object here is very similar to phi4, but there is also a deep difference. Phi4, for instance, in 0 dimension needs positive lambda here. Instead, the Grassmann integrals are analytic in lambda. Okay, so it looks very much like phi4, but are very different. For even in 0 dimension, this is an analytic function, simply lambda, and this instead requires lambda positive. So now I don't know how much enter in this. So the point is how now we, so what do we do now? So we got these expressions. So how we can solve this? So how we can study this? So luckily there is this big effort in constructive quantum field theory to study objects like this. So this class of models can be written in models which are very, you can study by the method developed for studying interacting Grassmann integrals. Okay. In particular, let me say 2 words and then I will pass to the results. So one could write simply to expand the V. Okay, that's the first stupid idea. Right? Simply expand this. Then you get a terrible bound because you will get G is the propagator, so you will get the infinity norm of G times the volume to the n. So on the other hand, this is expected because this should be the log of this is proportional to the volume. So if you expand simply this, you will get volume to the n, which is a very bad idea. Okay, so that would be a very bad idea. So if you do the simplest things, you get a terrible bound, n factorial G infinity volume to the n. So absurd, very, very bad. But then you don't have to expand this in this way. Then you have to expand the log. This is a very well-known trick. If you expand the log, the situation is much, much better. Okay, much better. It's better. So you will see it's a long path to get something you can do, right? So it's a path that people have struggled a lot. So first step, just expand the V. No, okay, so forget. You get n factorial G infinity volume to the n. So I cannot imagine something worse. So G infinity is infinite and factorial, so sorry, forget. Then let's try to expand the log. If you expand the log, then you write log of P in the psi, you can write in terms of what are called cumulants. Okay, the cumulants are much better. So this is a proportional to a single volume, not volume to the n. So if you expand these cumulants, you get n factorial square terms, which are the famous Pfaffian diagrams. So the bound, so each terms is not bad. You get a volume times this G1, G infinity, G is the 2-point function, times 1 over n factorial. But then, okay, so this is the bound you get. So the volume here is good, but then you have 2 big problems. First, the graph, you will get, so first of all, G1 is not finite at criticality. It goes like 1 over x, so the norm is infinite. So at criticality, you don't get the bound. But then also you get, in addition, you get n factorial terms. So the bound you get is this, not very good. N factorials max G1 to 2n. So G1 is infinite at criticality, and then you have an n factorial. So again, we have lost. So and now we lose, and we will lose, and we will lose until we get something. And we try and try and try, and hopefully we get something convergent, right? So now there is a very nice idea. These are determinants connected to determinants. So we need to use the signs, okay, the signs between the different terms. So now there is a very famous trick. This is also very old, the 70s, these Bridges, Battle, Featherbush representations. You can write the truncated expectation in this way. So the idea is you don't have to expand all the possible terms. You expand only the terms which needs to make the sum over the coordinates. And you leave a lot of fields here in the determinants. Okay, so these determinants are okay because you can bound them. Okay.
So what is T here?
This is the tree. So you will have, so T is a tree. So for instance, this I represent this psi tilde as fields. So suppose these are psi tilde are set of psi. So one could, the truncated representation means you should have to contract in all the possible ways these things. But this is bad because it has n factorial terms. Okay, so we do something better. We just connect by a tree, and we leave all the other fields in the determinant. Okay, so for instance, this is a possible tree, for instance. But then all these fields are not contracted. So this is the real power of this formula. But so in this way, you can bound the determinant. Okay. So this is is a set of lines connecting the cluster, which is not sorry, it's not exactly a tree because these points have different coordinates. Okay, so it becomes a tree if this circle becomes a point.
What is the declaration of the psi? You have the epsilon and x.
This can be okay. So maybe you can forget. In general, you can have two kinds of. That maybe is a mistake. Forget this. In general, you can have two kinds of fields. For example, in the Ising model, you have psi bar.
Oh.
But okay, you can forget. In the dynamics, you have only one, but in the Ising, can have two. Okay. So you see, and this dp is something which is bounded by one. So this is a formula which is very useful because you see. So now you get a good bound. Because now you have the sum over t gives n factorial, because you have trees now, not without loops. So you have trees, right? So you have factorials. The determinants gives you c to the n, because it's a gram term. Then n factorial cancel with the 1 over n factorial in the sum. So you will get a bound like that. Sum cn max between the g1 norm and the g infinity norm, lambda to the n.
What is your G? Is that your green function?
Yes, it's the green. I would not call it green function. It's the 2-point function. Yes.
Okay.
Yes.
But it has a slow power.
Yes. What? Yes. Of course. In fact,
It has a 1 over.
yes. In fact, we are still lost. Again, we have lost because if we are at outside criticality, then it would be finite. Okay, because then you have exponential decay in the Ising model. But at criticality,
So it's the L1 norm that you're bothered by, right? Because it has a slow
Yes.
power.
yes. So so the point is, if you are outside criticality, right, this would be finite. But that is not an obvious result. There are regimes, for instance, in the dimers, in which you have what are called gas regimes, right, in which you have exponential decay. Also, it's good for getting a bound. But if you have at the critical point, then you will
Then you have a poor decay.
and then you have to do something more complicated. You have to do this multi-scale expansion. Okay. So but before doing that, let me say, so I hope this formula is a very key step because it doesn't work for 5-4. Okay. Here we are really using that the determinant are more as bounded by Cn. I think the first one who said that is Caianiello in this, I think late 50s. It says that the series for fermions are much better, are convergent. Okay, but are convergent if this norm is bounded, otherwise not. Okay, so before using this, but this again is not useful because this G1 is not bounded. But then I will. Okay, so before saying that, let me say which are the conjectures. The conjectures are these conjectures are mainly due by Kadanoff. In the Ising model with the perturbation, the exponents do not depend on the perturbation. The critical temperature change, but not the exponents. Okay, so this is for the Ising perturbed Ising. Instead, in coupled Ising, the exponents are changed. This was a shock I think in the 70s because people believe that also if you, so right, you understand how much is strange. If you consider one Ising, lambda is the perturbation. So if lambda is equal to 0, it reduces to Ising. So in the case of one Ising, if you put the perturbation equal, so the exponent does not depend on the perturbation. But if you consider two Ising models, then it depends on the perturbation. This was clear because Baxter solved this 8-vertex model and was able to compute one exponents and the exponent was a fraction of the.
But this is a very particular coupling.
In all this cluster model change.
Yeah, but what I'm saying is that there's four body coupling between the two Ising models.
Yes,
They have
yes.
to have a special symmetry.
Okay, yes, of course you need it.
Otherwise,
Yes.
you're in the same universality.
Yes. In fact, it's even more complicated. Of course, I was referring to this case, right? But of course, if you need some symmetries for this thing. Okay.
Otherwise, it'll
Yeah.
be the same.
But there is a very wide class of models in which you have this, all these vertices, all these substitutes, and so on. Okay. But then, even in this case in which the exponent change, there is a notion of universality.
Sorry, I'm not sure if this is the right moment to ask the question, but is everything that you're discussing only for a square lattice? What if you try to take a triangle?
For the square lattice.
But what if you do triangular? How would it change, or would any of this apply at all?
Again, it depends on the symmetries. At the moment, it's just for the square. Can you hear me? Because I don't see you. So.
Yeah, I hear you. Okay, so you can.
Square at the moment.
So how much of this can you generalize to a triangular one, or is it like completely different with like Pfaffian and stuff?
I think of course you can change the lattice. It's not very. It's just what I'm saying now is for the. I'm just starting from the Ising and then considering other. But whenever you can have a solution for the triangle, you can make a perturbation, see what happens.
Could be the same
Okay,
thing.
thank you.
Yeah, I think it's, for example, we apply to several other ones. But let me say this very interesting conjecture by Kadanoff, right? So Kadanoff was sort of genius and just wrote these equations, the 77. So he said that the crossover exponent is the inverse of the energy exponent, and the polarization is the energy divided by 4. So it's a formula by Kadanoff is obtaining perturbation theory. You simply get here 1 plus lambda, here 1 minus lambda. That's it. And they say, so this means it's the inverse and is okay. So it's sort of, and then there are a lot of papers trying to, even by Kadanoff himself, to try to prove this. Because of course, if you look these two series, are very complicated series. You can verify this relation at first order, but not more. So how you prove this? So all these are conjectures which are difficult to fix. So let me say the result. So the first result using this Grassmann integral is by Pinson and Spencer in 2000. And they proved that the exponent of the Ising model is 1. So the case is 1 over x squared, while the critical temperature varies. Okay, so this is, I think, the first result. And that's it. And then in 2002, I was able to compute the case of coupled Ising models with the same J. And then in that case, I was able to write a convergent series. So in fact, it was quite easy for me because maybe this is not very interesting, but I didn't know how to write this Grassmann integrals, this coupled Ising. So I learned from Tom that, and then I already did all the theory with the group in Italy. We already studied a lot these Grassmann integrals with interaction. Since I didn't know how to map the Ising model, so he taught me that, and then in 1 month I missed just this very step that I was very happy to learn. I was trying because now that I know it's very simple, but there are other ways in which you can get this Grassmann integral. For instance, you can pass through Lieb, Schulze, and Mattis, getting creation and annihilation operators, and then so on. So instead, okay, that was the results. Then with Giuliani, we consider Ashkin integral with different exponents, with different J, and we discover a new exponent. So even the difference of the critical temperature scale with the critical exponent. So all you see from this is up to this point, it's very difficult to see any universality relation, right? Because here I should compute all the series to see this Kadanoff relation. So finally, in 2009, we were able to prove 2 of this Kadanoff relation, this one and this one. Okay, I will say maybe 2 words how we were able to prove. Okay, and then also we compute the central charge. So these are results up to 10 years ago. So as you can see, the universality is only in not for extended quantities. So the universality is only for the energy. For the energy of the crossover or not for the spin-spin. The spin-spin is much more difficult. And you see why, because in the fermionic representation, the class representation, you have to make a sum over time. So at the moment, one of the challenging problem is to compute this approach, the quantities which are extended, okay, like spin-spin correlation. So the only result in this relation is the one I'm telling you. We consider the dimer. Then if you consider the interaction in the dimer correlation, then you get an exponent here and not an exponent here. Okay, so this is not one. This instead is one. This is very important because the height function is the sum over that. So you see, if the height function takes contribution from this, then it would be a disaster. It would be not anymore a Gaussian term, because now it's not the singularity would be not 2. But due to this sign, this contribution disappears, and only this part remains for the height. So this is the best we can prove for extended quantities. We could prove that the height correlation is still Gaussian, so these surfaces generically are Gaussian fields. But then there is a universality relation. This A, the amplitude, is eta 1. Okay, so this eta 1 here is exactly this A here. So for a certain time, we were surprised. So this is work with Giuliani and Toninelli. So for a certain time, we were said, okay, we have found a new relation. So very good. So we're very happy we found something new. But instead, after we realized that is the second relation, if you assume this relation, which we cannot prove, that exponential of the 8 is equal to this, which is very natural to assume because it's Gaussian, but we are unable to prove. But if you assume this is exactly the second relation of Kalanov, connecting the polarization with the energy. Okay, so this is the sort of, so this is exact defining A and eta 1. Okay, I'm sorry, but it is very much related to the, so at the moment we are still unable to prove, to make this step, that to get this other relation, but this relation is interesting by itself. Okay, and maybe I can say 2 words about what is called bosonization. So bosonization is a way in which you write quantum field, you write a couple of fields in terms of derivative of Gaussian fields, fermionic fields in terms of derivative of Gaussian fields. So this bosonization, you see, if you couple this, you get the exponential. If you couple the same omega, you get the derivative. So this is simply Cauchy determinants, but the conjecture of physics is that this should be true. In fact, it's true in certain cases, also with interaction with a different A. So if you assume these simple rules, okay, then the result I show you is a one line. Okay, so this gives support to bosonization. Right? So you can write the dimer in this way, and then if you use these rules, this became this, and this became the exponential. So you see, this exponential, it becomes e to the a log. So the exponent of this part is simply the amplitude of this part. That is exactly consistent with bosonization in the generic case. Okay. So I don't know if, so of course, so the question is, does exist, so exists a discrete bosonization holding even when you don't have a solution? Maybe yes, but you see, the implication of bosonization are true. But I don't know, these formulas are in the continuum, so who knows? But it's strange that you make exactly the correct prediction. Right? So it's, I think. Okay, so if maybe I can mention another result. You can even add a quasi-periodic disorder, for instance. This is a very recent result. Then you can add Diophantine to the Ising model. Then you can impose some Diophantine condition on this. And then this is similar to KM now. You have Diophantine condition in commensurate terms. Then you use the fact that you can prove by inequalities like this that the interaction is irrelevant. And in fact, is a paper by Grassmann and Mastropietro in preparation that we can prove that this perturbation is the same. That doesn't change the exponents. Okay, this is more or less the result. I don't know how much time I have. 5 minutes.
About 10 minutes. Yeah.
10 minutes. But well, maybe I can say 2 words on how these results are proved. So as
So wait a minute, let's go back. So the statement with this quasi-periodic. So you,
yes, of course.
so you have a Jij, which is quasi-periodic.
Yes, with 2
But it's
frequencies.
a small quasi-periodic.
It's a small,
basically.
very small. Yes. It's like in KM, small. Yes.
Okay, and then.
Then the problem is if you have, so the dangerous term is when you have the same momentum, same K. Now you see, if as omega is irrational, then this omega n could be closer and closer to 0 up to 2 pi. So you have terms which are almost relevant, but not really relevant, right? Because if omega n is very large, then this is very small.
So then there's a critical temperature again.
Yes, the critical is changed, but not
It
exponent.
will change.
Yes,
But the exponent, the
Doesn't
specific heat is still logarithmic and all that.
exactly. And it's exactly is in KM. You have an accumulation of small divisors, but then you use the fact that it's true that omega n can be very small, but then n must be very large.
But does this use Grassmann variables? You don't need Grassmann.
Yes, I always need. maybe you can avoid, but I only use Grassmann variables.
So you can explain how you use Grassmann variables other than through a formal manipulation. Do you actually analyze asymptotics of these determinants?
Maybe you can, but so for me it's very easy because if you pass Grassmann, so what?
So now you have a Dirac operator, and then you got.
Yes, maybe it's possible, but I did this. I simply consider this. I consider this sort of CK plus n. Then expand this, and then I get this very simple graphs, very simple.
What are you expanding? You're expanding the quasi-periodic?
Yes, expand the quasi-periodic, and then I get yes. Then I get a series of propagators, and then I bound in the usual way. But well, for instance,
But let's say in the previous theorems, your older theorems,
this is what I do always.
A lambda being
This is
analytic.
quadratic. In fact, in principle, it's not necessary. Of course, one can study the operator and try to. Yes.
You do the same thing? I mean, how do you get that function that's analytic in lambda and its behavior? I didn't understand. You stated a theorem.
Yes.
You put on the perturbation.
This one?
Yeah.
Yes.
So how are you using Grassmann variables?
Yeah. Okay. In this case, yes. Let's see.
Not
Yes. So we do this. We make multi-scale analysis. So we start from an object like this. Okay. So as we said, if I simply expand. So as I said, let me say 2 words on how these are proved. Also, I will tell you how is proved the result of Tom. You don't know if I succeed in 5 minutes. Okay. What is it there? I don't find that. So the first observation is this determinant bounds, right? So where they are.
Okay, so that's one use.
Okay. So the first point is this. Then one could do that. The log is expanded in terms of these truncated expectations. And then these truncated expectations are written using these formulas. By these formulas, I get a bound in which if the G1 norm of the 2-point function is bounded, then it's finished. The problem is that the G1 norms is not bounded. So what we do? Instead of integrating a single step, we do several steps. So this is exactly what is called renormalization group. So you use the additive properties of also this Grassmann variable, so this one, also this, sorry, it's 2. I think it's the mess. It's 1, 2. So also these Grassmann variables, these are exactly the same rules which holds for Gaussian integrals. So here there is some tip. If you write the covariance, the sum of 2, you can integrate by steps. You can integrate first the field psi 1 and then the field psi 2. Okay, so there is some mess here. This 2 and this. Sorry. Right. So this 1, 1, 2, 2. Okay, so I integrate one fields and then the other fields. Okay. Okay, and then you use this other relation. Okay. Then the covariance is written as sum of infinite many covariants, which have the scale size gamma to the h, and h is smaller and smaller. And then we integrate step by step, and then we get a sequence of terms. Right, so you start from this, then you decompose, you integrate the first, and then you get 0, and then you decompose again and again and again. You cannot do in a single step because the norm G1 is bad. So now, after the integration of psi0, you get an expression similar to the initial one, but now you have several terms, and then you have to do something. Each single step is good because we use the determinant bounds we have seen before. But now the radius of convergence would shrink to 0 if you don't do anything. But now, okay, then you use these Galavotti trees just to order. And now there is a great difference between perturbed Ising, which is the case of Spencer and Spencer, and the case of coupled Ising models. In the case of Spencer, the local part of the quartic term is 0, right? Because you have two fields in the same point. So this says that you don't have this non-trivial fixed point. Okay. While instead, in the case of two coupled Ising models, this object here would be non-zero. So that's so in the case of Tom, you want what was which is the Ising model with the perturbation. What one does is you make a first integration, then you make something which is called dimensional analysis, which tells you under this normalization group map if some of monomials increase or decrease. The terms which decrease are called irrelevant, are okay. The terms which remains equal are these quartic terms. They are called marginal directions. But these marginal directions are indeed irrelevant thanks to this cancellation. Okay. And this more or less was the result of Pinson and Spencer. Instead, if you consider Q Ising model, then you have an extra index here. So it's non-zero. Then you have something much more complicated because then now you have what are called random coupling constants. And at the end, you need, so I will not say that much on that, but you need a lot of symmetries to control the quartic part in the case of choosing model. But at the end, you get an analyticity. I can say 2 words how we prove that this is a result which is called vanishing beta function. It means, so the idea is that, so I can make it say quickly the idea. The idea is to compare the model, maybe, and then I stop here, we became too technical, but there is also connection with anomalies. There is the book which Joy took to me. There is a very important connection with anomalies. I don't know if I have time to say. Anyways, the technical idea is you make it now for the proof of the coupled Ising model, right? So you introduce a model like this, you invent a model, which is still a Grassmann integral. This model has more symmetries because it has what are called chiral symmetries. And using these extra symmetries, these symmetries are not exact in the lattice model, are only emerging, are approximate. But to use the fact that there is a closed model, which is instead has exact symmetries. Using these exact symmetries, you can, in a sense, solve this model. But what is important, you can prove that you can fix parameter of this model which you invent so that the exponents are the same. So the trick is, I invent a model which has the same exponents if I choose in a proper way the parameter of this model. Okay. So I tune the parameter of this model so that the exponents are the same. But this model has more symmetries, and I use some exact solution of this model. So you don't need really the original model is solvable. You need simply that the emerging model is solvable. Okay, so that's more or less the.
How do you prove that they have the same exponents?
Yeah, because you make the same renormalization group analysis, multi-scale analysis also for these models, and then you see that they differ by terms which are irrelevant, so which are summable. So you can tune this parameter here, z, zeta 1, and so on, so that all this random coupling constant has the same fixed point. Okay, so it's yes, this is a crucial point. In fact, we don't use any exact solution. We do again the same renormalization group analysis, and we compare the series are very similar up to subdominant terms.
Yes, it's almost as if you're coupling a renormalization group on both of them and showing that they converge to the
Yes,
thing by
yes,
subtracting.
Yes, it's a line of fixed point, so it depends on the parameter of the model. So if I tune them, so I have the original model which has a fixed point. The other model is another fixed point, but I can choose the marginal direction of the new model so that the exponents are the same.
But the point is that whenever you reapply this normalization group, they get closer and closer together.
Yes, they're closer because the terms are, the difference is irrelevant in the normalization group set. In a sense, it's like to say I'm doing the scaling limit. Right? So this model is a continuum model. In a sense, is the scaling limit of the lattice. So when you are closer and closer to the critical point, the lattice is less and less important. So I can, but it differs of finite quantities. Right? So what I want to stress is that this Z are series. So it would be, it's very, okay, anyway, I have to really careful to choose this parameter as a function of the original model to have the same exponents. So that's is the idea. And now this model can be solved. So I finish here because there is maybe the most nice point is here, that this model is solvable and I get the exact expressions for the exponents and also for the amplitudes. But then I have the Z. So the Z are bad if I want to compute the universality properties because are series which are very complicated. I don't know anything about that. But then I use the other word identities of the original lattice model to get other conditions so that I have a lot of conditions of these parameters, which I know a priori that are only finite. But then I have also some self-consistent information of the Z, which allows me to prove the universality. Okay, that's more or less the idea. And I finish saying that it's also, I use another property which is called non-renormalization of the anomalies. So this model has anomalies which are exact. That's also very important. I need some object which is exact to say something on the exponents. Okay, if I have series and I finish by that. So if I have only series, I could never prove this relation.
Just to be clear, something.
Yeah.
You have this. Your A lambdas are given to you by a convergent series.
That's it.
And that you know nothing about because it's just a mess. But now
It's very complicated. More than the second order, you cannot compute. So I tried, but I tried. So I tried a lot to prove really that all the terms match. That's impossible. So I need a new idea. Otherwise, by series, I can't. I know only they are convergent. So if I stay only at the level of series, I get this poor result here. Right? So it's simply this. That is 1 plus lambda.
yeah.
Right. So only this. Okay. So I know that this is convergent, but I need to prove that the product of this by this, for instance, is 1. Okay. So how can I do that? I cannot compute all the exponents. It's too difficult. Then I use this idea of this other model, tuning the parameters, getting extra new symmetries by this model. I get a lot of algebraic relations. Okay. Which maybe I can show you. It's not so difficult. So it's just. Maybe otherwise seems too magic. I show you just as
these are symmetries or approximate symmetries of the system.
Yeah, they are approximate symmetries for the system, but exact symmetries for for this model which I use. So you see, so just to finish, I get maybe this is the last formula. I get a formula like this, for instance, which is essentially this A. So you see this lambda infinity is a series, the zeta 1 is a series, this Z is a series, everything are series. But then I get some consistency relations for this one, because I know that I compare word identities in the lattice model with the emerging, then this is really the idea of quantum fit here. Not all the parameters are independent. There are relations. And by this relation, I can simply get that. Okay, so at the end, I need some algebra to close this. So that's more or less the idea. Okay. I don't know if
so Vieri, I mean, for me, the Grassmann integrals are useful because they're a very useful way of encoding the interaction, right? As a quartic term, right?
Yeah.
So you're very used to the quadratic term, which is determinant.
I hope it was clear by the talk. Right?
I just want to try to summarize a little bit.
Yeah, I hope that's supposed to.
Yes. So you have quartic terms, and then and these quartic terms, of course, make the theory not soluble, but you can still use some kind of renormalization group analysis to show that they, to some extent, they're irrelevant. Right? And sometimes they are relevant. And sometimes
in this case, are marginal, but then I use, in your case, were irrelevant.
Yeah.
In this case, are marginal, but still I use, then I need to use this sort of idea that are marginal, but symmetries of the emerging theory allows me to I need some sort of.
And the height functions you refer to over here, and well, we know they're Gaussian, they're free fields, they're Gaussian free fields with.
It remains free fields.
It remains free fields in your picture, even with
Remains free
interact.
field, but exponent change.
So it's kind of a central limit theorem that tells you
Yes,
that
it's a kind of
you
central limit.
remain,
Yes.
that you remain.
But,
free
yeah, or Botulization, but the amplitude of the free fields, of the height function of the Gaussian fields change.
Yeah.
Becomes non-universal, but still it has this
It's
universalization, which
it's
is
still Gaussian.
it's still Gaussian, but still, yes, it's still Gaussian, even if it is not free fields. Okay, so it's so in a sense, I just repeat what you say. So in the free case, you have this Bosonization, but this Bosonization is simply Cauchy determinants.
Yeah.
Okay, so in a sense, it's a trivial. It's just Cauchy determinants. But if you have interaction, it's still Bosonization is true. Still, you can describe this option in terms of free fields, even if you don't have any more Cauchy determinants.
That's certainly not obvious, but how that.
I hope it's not obvious. Yes, yes,
Yeah.
it's not obvious at all, right? But this is the power of Bosonization. Bosonization is not useful in the. It's useful, but in the free
But you
case.
don't use Bosonization directly. You work all with Grassmann variables.
In fact, this is your dream since ever. I mean, this suggests, you see, I understand the point. I mean, you see, this relation that makes this big effort, you derive in one line. Okay, so in fact, I put this against me. Okay, so it's so it should be another way to get that. Of course, maybe I cannot find. So you see, in one line you get the things. Here you get exponent, and here you have A. So if you assume this, so the point is, if you assume that this relation also always that this is the derivative of the Gaussian fields, and this is the exponential of the Gaussian fields, then immediately you get the relation. So it's true in some sense, but I cannot prove directly this picture. I need to pass you too. we need
stay within the Gaussian, you stay within the Grassmann world.
Yes, but maybe there is a way to avoid this Grassmann world and go directly to this step. That's but at the moment, all the results I know are only for the free case without interaction. But all the point would be to see if a representation like this would be true generically, respectively or interaction. No, that would be the power of the. But that is Kadanoff, by the way. There is a paper by Kadanoff Brown, so also the 70s. He simply derived his relation by this. That's it. It's very easy. You make the continuum limit, then you write this. But just to make this rigorous, I don't know how to do.
Okay, any comments or questions?
I have a funny comment because when you go to these computer science talks, I always talk about the determinant versus the permanent. And you are going from the determinant to the Pfaffian to get at that cancellation. And of course, they emphasize how determinants can be computed quickly, but permanents cannot. That's sort of the complexity. So somehow it's kind of a similar thing. Permanent, there are no signs at all. Permanent, you have the signs, and the Pfaffian is the other square root.
Yeah, but it's not the case because they want really to make computation.
I'm just saying it's.
If you do computation by hand or by the computer, you get.
No, you don't want to write down all the n factorial.
Yes, for the factorial.
Good to see. In the Ifitoch method, you ever in this, I mean, Tom and I, well, at least I, the only exposure I have to this Grassmann variables and the supersymmetry method to do random matrix theory, you get, you use this to write down eventually like, you know, the sine pi x over pi x determinantal kernel that comes out of universality, comes out of a 8-dimensional critical manifold from these variables. Does that ever come up in this theory? I mean, Tom knows this very well.
Yeah, but he used for disorder, I think, right? So if you want to add a disorder, then the next step to that is to add a disorder. If you want to add a disorder, then you pass to this supersymmetric.
But again, those supersymmetric variables are the ones that allow you, it's the same theme.
Yes, it's the same, but then you have also bosons. So in fact, I think one of the main goals of this is to put together, I think still no one is able to do, put together bosons and fermions and then make a multi-scale analysis for both. Okay, for both together. Here you see you have only fermions. There are techniques for only fermions, only bosons. If you put, but this is the real life. In a sense, the real life, the real models which are interesting are, as you said, bosons and fermions together. like quantum electrodynamics, all the theory of physicists, you should do that not only for bosons and Grassmann. This is something still not many people is doing, but I think is the next year will be the main goal of these people, because it's me too. I mean, we need really to put together bosons and fermions. Otherwise, the real world is like that. So it's not the case. So this is too much too simple. Oh, sorry, I agree. Yes.
Okay. Thanks very much.
Okay, thank you very much.